Hello, everybody. Today's lesson is on pyramids of energy. It is our second part of IB topic 4.3, our second and only day. Yesterday, we spent time looking at how energy flows through ecosystems in a one-way direction, comes in as light energy, and leaves as heat energy. Unrecyclable. We cannot turn heat energy back into chemical energy. It's dead end. From 4.1, quick reminder that we had looked at how matter cycles. Energy flows, but matter cycles. Carbon just goes round and round and round as glucose as CO2, as glucose as CO2, as glucose as CO2, as one example. This first slide shows a conceptual pyramid of energy. It's conceptual compared to the next slide you'll see, which is quantitative. A little uglier, but the size actually depicts the amount of energy. Let's stay with the conceptual for a moment, just to get an idea of how these things work. What you're looking at on the base of the pyramid is our largest amount of energy stored in our primary producers on Earth in a given ecosystem. The next longest, but definitely shorter, it's not as long, are the primary consumers, all the herbivores that eat the primary producers. Next level up the pyramid, and it is shorter still, are the secondary consumers that eat the primary consumers, our first carnivores. Then, if an ecosystem has them, we have tertiary consumers, smaller still, less energy, because they have to eat the carnivores that ate the herbivores that ate the plants. Finally, if the ecosystem has it, you may see quaternary consumers. The idea here is that every single level up is smaller, because there is less energy in that level of the ecosystem. There is less energy because energy has been lost all along the way. All of these organisms need to accomplish functions of daily cell life. They need to create proteins, create storage molecules for fats, for starch, carbohydrates. Their enzymes are constantly working and facilitating chemical reactions, many of which need ATP to function. DNA synthesis, mitosis, meiosis, any of these require lots of ATP. When these organisms go through the daily functions of life, they need to make the ATP first in cellular respiration. That will lose some heat. When they convert the ATP into whatever form of work needed to happen, they lose even more energy as heat. Constantly lose heat energy with every transformation of energy. The rest of the energy is lost because not every plant in an ecosystem gets eaten by an herbivore. Not every herbivore gets eaten by a carnivore. So plenty of those organisms they die. They're not an actual calorie source for the next level up, trophic level up. Additionally, each of them, despite eating plenty of calories, they actually defecate a lot of calories out. So some energy is lost as weight. You can prove that by please don't, but dry out some poop and then burn it. Plenty of places do use this as fuel. They'll actually take cow patties, dry them, and burn them. That burning is release of energy, so you can tell that there's extra energy still even in poop. That waste and dead matter will go towards decomposers, who will do the final release of energy as they break down those molecules and release the rest of the energy as heat, and release some of the molecules like nitrogen and phosphorus back to the primary producers. All right, let's zoom into the less pretty version of this, quantitative pyramid of energy. So in the quantitative pyramid of energy, quantitative meaning quantity, the length of the bar actually is going to represent the amount of energy in that trophic level. So you should see that each bar is about 10% of the size of the one before it. Because of this rule of 10, it is a generalization in ecology, not a dead set rule, but typically most ecosystems only can support the next trophic level up at about 10% of the level of the one before it, because only about 10% of the energy from one level is available to the next, which is available to the next, which is available to the next. So about 90% is lost at each trophic level. Again, that's lost as heat, that's lost as waste and dead matter, which is eventually lost as heat. Let's create our own. To create your own, the IB would expect you to be able to give you some data, and then for you to calculate the size of each bar, and then graph them out. First, you have to choose your scale. For example, 1 centimeter equals 1,000 kilojoules or kilocalories per meter squared per year. So kilocalories or kilojoules, that's the actual energy. Meter squared means a 1 meter by 1 meter plot of land. Per year is, how many organisms go in and out of that plot of land per year. Accounts for growth and accounts for migration. All right. I'm going to create a different scale. It does not matter what your scale is, you just want to say it. My scale is going to be 1 millimeter equals 2,000 kilojoules per meter squared per year. Decide on your height. I will do, instead, I'm going to do 10 millimeters. 20 is fine. 2 centimeters, doesn't really matter. You just gotta want to say what you're going to do. Next, create a table to organize your work. I have already done that right here. Calculate the length of each bar. To do that, you need energy at trophic level multiplied by the scale. So here's my energy in column number 2. And my scale is up above. If I write that as a conversion factor, I would say 1 millimeter over 2,000 kilojoules per meter squared per year. And that way, when I multiply this conversion factor by my amount of energy, I can cancel out my kilojoules per meter per year. So 240, 1 millimeter over 2,000 kilojoules per meter squared per year. Units cancel. And move the decimal place over 1, 2, 3, and divide by 2. Or use your calculator. You will get 0.12 millimeters. Do this for each of them. 3,200 times 1 millimeter per 2,000 kilojoules per meter squared per year. I get 1.5 plus 1.6 millimeters. 14,000 times 1 millimeter over 2,000 kilojoules per meter squared per year. Seven millimeters. Do the last one. 150,000 times 1 millimeter per 2,000 kilojoules per meter squared per year. Gives me 75 millimeters. All right. So here are the size of each of my bars. Producers will be 75 millimeters long. My primary consumers will be 7 millimeters long. My secondary consumers will be 1.6 meters long. And finally, my tertiary consumers will be 0.12 millimeters long. So here we go. Need your ruler. I'm going to try this digital one. I'm sorry for the couple mistakes I'm probably going to make in trying to figure out how to make this digital ruler work. I want my producers to be 75 millimeters, which is 7.5 centimeters. That is a little off. Oh well. If you got a real ruler in front of you, this will be a lot prettier than my digital version. But it's good enough. Primary producers. Now, bring that up. And I need my primary consumers. My primary consumers, I want to be 7 millimeters. Seven millimeters is only 0.7 centimeters. So it's going to be very small. Yeah, like I said, sorry for my inevitable mistakes with this new learning tool. You want to center that, and these are your primary consumers. All right, next up, 1.6 millimeters. So that is teeny, teeny, tiny. What color did I use? Orange? We'll do orange. So 1.6. It's almost 2 millimeters. Center that guy, label it secondary consumers. And the last one is too small to graph, 0.12 millimeters. I cannot graph that on here. Here's 1 millimeter. Not going to happen. So if it is too small to graph, then you just want to draw a single vertical centered line. And just make sure it's centered. And then label that tertiary consumers. All right, ideally that'll be a lot easier for you with a ruler, and you can center those and angle those, give it a title, pyramid of energy in X ecosystem in some year, because this will change. Key, make sure you get your scale in there. And we chose the scale of 1 millimeter per 2,000 kilojoules per meter squared per year. And there we go. There is our quantitative pyramid of energy. Sorry, it is not as pretty as I wish it was. Try the practice problem. I've got an in-thinking worksheet on there for you. You can do it on a blank piece of paper. If you have a printer, you can print it. Good luck with these. Post any questions you have for me.